Hey, good evening, AP Physics students. Mr. Gerson coming at you here. We're going to talk a little bit about circuits and batteries today. Starting out with example problem number 1 from Chapter 19. Let's dive right into it. Chapter 19 starts to talk batteries in a real sense. So here I have a battery, right? What is one? Well, they're not perfect things that physicists sometimes want them to be. And the way we model how imperfect they are is we say that batteries are a perfect voltage source or have an EMF and then an internal resistance. So here this Greek letter epsilon, I think it's a capital letter epsilon, is short for EMF or electromotive force. And it's when you hear that term, you're going to want to think voltage, but specifically the voltage of a battery or the perfect voltage of a battery. And like I say, we model batteries as having a perfect voltage, but then also an internal resistance. Batteries, if they draw a lot of current, can actually heat up because of their internal resistance. This might be what happened to the Boeing 687 that was starting on fire, which caused them to get grounded. Right? So that's what I want to say about voltage. Now, EMF is the perfect voltage of the battery, and then the terminal voltage is the voltage between the terminals that takes into account the internal resistance of the battery. Okay, so EMF is like the perfect voltage they would have. The terminal voltage is the actual voltage they have while taking into account their internal resistance. So that's a little background there. Let's dive right into this problem. This problem states that I have a battery with an internal resistance of 0.9 ohms, an EMF or voltage, perfect voltage of 8.5 volts. What would its terminal voltage be? So here's what I want to do. I want to calculate how much voltage I lose between the terminals due to the internal resistance here. So I'm guessing that I might lose just a little bit. But let's find out how we would do this. Well, the first thing we need to do is calculate the equivalent resistance of this circuit. And for two resistors in series like this, the equivalent resistance is you just add them up. Okay? So what I might do is rather than model this circuit as a battery and two resistors, I could redraw this circuit like this. A battery of 8.5 volts and then a one resistor instead of two. And this equivalent resistor would have a resistance of 81.9 ohms. How did I get that? Well, I added these two up. Now, this is for resistors in series. Okay, the formula for resistors in parallel is the inverse of that formula. Remember, resistors in series, the current goes through one resistor and then the other. There's kind of only one path for the electricity to go through. Okay, so let's calculate the current that would be coming out of the battery here. Remember, current leaves the positive terminal, goes into the negative terminal. So let's calculate the current in this battery, coming out of this battery. Well, that would be the perfect voltage, 8.5, divided by the equivalent resistance. And if I divided that out, I would get a current of 0.104 amps. Okay? So 0.104 coulombs per second of charge is coming out of that battery. Now, how much of this voltage, though, gets lost across this resistor? Well, to figure that out, we're going to use something called, talk about something called Kirchhoff's loop rule. All right? So Kirchhoff's loop rule states that the sum of the potential changes around a closed loop must be 0. And that's worth writing here. The sum of the potential changes around a circuit must be 0. Now, what does that mean? It means if a battery bumps up the voltage in a circuit 8.5 volts and there's 2 resistors, then each resistor takes the voltage down a notch, and the total voltage downs should equal the voltage ups. All right? So, how do I figure out how much voltage is lost across this little internal resistor? Well, I could do that by rearranging Ohm's law, and this time I'm just going to calculate the voltage drop across this guy, across R1. Well, this would be equal to the current in the circuit, 0.104 amps, times just that resistance, 0.9. So if I round this out a little bit, I get the voltage drop across resistor 1 here equal to 0.09 volts. All right. Well, if this battery has a voltage of 8.5 volts in a perfect world, and I'm losing a little bit of voltage as I go through this internal resistor in the battery, what would be the terminal voltage? Or if I put a voltmeter across the terminals of the battery, what would that be? Well, so my terminal voltage, or the voltage between A and B, would be equal to, my perfect voltage, or my EMF, minus the voltage drop across that internal resistor. In other words, this would be 8.50 minus 0.09, or the terminal voltage would be 8.41 volts. So you can see with a reasonable current coming out here, my terminal voltage is almost the same as the EMF of the battery, but not quite. Now, if I get larger currents, that terminal voltage can vary quite a bit. Now, this was part A of problem 1. I'm going to have you work out the answer to part B, where they change this resistor to a much larger resistor, and see if the same result is valid. All right, nice work, AP Physics students. For your fun thing today at the end of the video, I don't have something crazy exciting, but this is just a little bit of history here. Back in the day at Jefferson High School, I was a trumpet player, and this is a really old certificate from the state music contest saying I was in a trumpet duet and got an excellent rating in April of 1991. That was a long time ago, but something goofy that my mom found for me. So, there you go, AP Physics students. Nice work. We'll see you tomorrow.